If math has been driving you crazy, or if you're finally admitting you're lazy, and your test grades have been dropping, it's time to get your arrows popping.
Ladies and gentlemen, this is Mr. Witt with Fort Bend Tutoring, and today we have another tutorial going over inverse functions. That's right, inverse functions. That's what we have. And before we get into our festivities today, please go ahead and subscribe to our YouTube channel, Fort Bend Tutoring. Go ahead and click on that bell icon so that you can be notified when we're uploading new and fresh content. Go ahead and click that. Thank you. And I want to also give a shout out to Elias Flores. That's right. That's my boy. He did the intro. If you like the new intro, guys, give him a shout out in the comments. Appreciate that, Elias, my boy. Let's get into the lesson where we have inverse functions. That's right. And I have some fun facts to bring to your attention. Starting out with fun fact A. Every one-to-one function has an inverse function. B. The line y equals x is the line of symmetry of inverse functions. That's right. C. If f and g are one-to-one functions and f composite g of x equals to x and g composite f of x equals x, then f and g are inverse functions. In fact, one can say that if f composite g and g composite f both equal to the identity function, then they are inverse functions. Fun fact D. If f of x is a one-to-one function, then f to the superscript -1 of x is its inverse function. And one can call this labeling f inverse, or you can call it the inverse of f. That's what that labeling means. And please note that the -1 is not an exponent and is just a part of the label for the inverse function. So don't confuse that with an operation. It's just a label that means the inverse function. That's right. Fun fact E. The inverse of a function can be found by exchanging the domain and range of a one-to-one function. Good to know. The graphs of inverse functions. There's a relationship, guys, that if you start out with a linear function, then its inverse function will also be a linear function. If you begin with a quadratic function, its inverse function will be a square root function. When starting with a cubic function, its inverse function will be a cube root function. A quartic function will be a fourth root function, and a rational function, when finding the inverse, it will be a rational function. An exponential function, the inverse of that is a logarithmic function. So it's good to know when starting out with either of these functions that its inverse will be in the forms that you see notated here. All right, let's move on. In number 1, it says to find the inverse of the function. Well, what I have before me is a function. How do I know this? Because I have a set of ordered pairs where the x values do not repeat, and it's a one-to-one function because all of the x values are different and because all of the y values are unique, aka different. And based on one of our fun facts, anytime you switch your x and y values of a one-to-one function, you will end up with the inverse function. Therefore, my inverse function is as follows. All I have to do is write it as 8,3. That's the first point. -2,4. That's the second point. What did you say? Oh, you already know what the third point is? Yeah, it's going to be -3,5. You're exactly right. That is all it takes to find the inverse of a function. That's right. Just switch the x and y values. That's it. Oh, yeah. By the way, red box it. Put a box around the answer. Oh, yeah. It's over. That's right. That's all you had to do. Yeah, they give you a set of ordered pairs and they ask you for the inverse function. Just switch all the x and y values. That's it. You're welcome. Let's move on to the next problem, shall we? Problem number 2. It says determine whether f of x equals 3x minus 4 and g of x equals x plus 4 divided by 3 are inverse functions. Well, there's a way to do this algebraically, guys. Now, we could graph it and see if the line y equals to x is a line of symmetry. We could do that, but I don't like to graph. So we're going to go ahead and find out if the composite of f and g of x, if this is going to equal to x, as well as g composite f of x, if that also equals to x. Because if they both do, then we have verified that these are inverse functions. So recall that this composition means f of g of x. Well, what is g of x? G of x is x plus 4 divided by 3. So what we'll do is we will be replacing every x in f with the quantity of x plus 4 divided by 3. So what does that look like? It'll have 3 times the quantity of x plus 4 divided by 3 minus 4. Okay. And then to simplify, we'll have the 3's canceling out. So you'll have x plus 4 minus 4. And once the 4's cancel out, this equals x. Yeah, that equals x, guys. So we're looking to see if G composite f of x equals x also equals x. So remember that this means G of f of x. And that means that we would be replacing every x in G with the quantity 3x minus 4. Okay, so how does that look? Well, it looks like this. You would have 3x minus 4 plus 4 divided by 3. So notice that in the numerator, your 4's would cancel out because those are additive inverses. And you'll have 3x divided by 3. And what happens here? They cancel out. So this equals to x. And since both f composite g of x equals to x and g composite f of x equals to x, then this verifies that both f and g are inverse functions. So the answer to this question has been resolved. And we could just put a big fat yes right here. Red. Box it. Got a box that is red around the answer. There you go. So that's all you need to do when asked to determine if two functions are inverse functions. You can use the algebraic method of using your compositions to see if they both equal to x. Let's move on. And I want to remind you guys to set up a paid online tutorial today with Fort Bend Tutoring. So all you got to do is go to our website, hint, hint, and you can set up an online tutorial with me. Yeah, and I can help you out with your math and stuff. That'd be cool. You, me, and the math. That's what I'm talking about. Let's move on. In number 3, we're asked to find the inverse of the function. Well, there's a process for this, guys. The first thing you want to do is you want to take the equation out of function notation. So you're going to rewrite this as y equals 1/2 x minus 3. Your next step is to switch the x and y variables. So we'll rewrite it again as x equals 1/2 y minus 3. Your final step, guys, is just going to be to solve for y. So in solving for y, I'm going to add 3 to both sides. Let's do that. Okay. This will allow me to rewrite it as x plus 3 equals to 1/2 y. So then I can multiply both sides by 2 and have 2 times the quantity of x plus 3 equals 2 times the quantity of 1/2 y. What happens on the right side is that the 2's will cancel out. And we'll have y equals, if you distribute, 2x plus 6. That's right. I got my arrows popping. That's right. Arrows were a-popping. So after you have solved for y, you're going to write the result in inverse function notation as f to the negative first of x equals 2x plus 6. Yeah, just like that. So as far as simply solving the problem, this is the answer. Red box it. That's right. Put a red box around your answer. That's right. Be loud and proud about the correct answer you have now. Moving on. We can also graph this. Yeah, let's go ahead and graph this. Let's see what's going on. In fact, in order to graph this, I'm gonna show you something. Knowing that these two are inverse functions now, remember this is our original function for problem number 3, and this is the inverse function that we just found, right? Let's choose values for x in the first equation. We're gonna make an xy chart here, and I'm gonna plug in values like I like 0, yeah. And let's go ahead and choose -2. That's a good one. And what about 4? Let's go ahead and do 4. So plugging these values into the original function, guys, we know that 1/2 times 0 is 0, right? And then 0 minus 3, well, that gives you -3. Okay, great. Then with -2, what happens? Half of -2 is -1. And -1 minus 3 gives you -4. Yes, it does. Then let's plug in positive 4. Half of 4 is 2, and then 2 minus 3, oh, that gives you -1. That gives you -1. Yes, it does. And the beautiful thing about this, guys, is, let's go ahead and graph this. We have 0, -3, 0, -3. That's right here. Thank you. And then you'll have -2, -4, 1, 2, and then 1, 2, 3, 4. That gives you a point right here. Yes, it does. And then let's go to 4, -1. 1, 2, 3, 4, -1 gives you a point right here. Great. And so in graphing this, boom, boom, there we go. There we go. Yes, better. There we go. Yeah. That is the graph of f of x. Now, when it comes to you graphing the inverse function, you don't have to start your XY chart all over again. No, you don't have to do that. In fact, all you'll need to do is switch out the X and Y values. Remember, once you have the ordered pairs from your original function, in order to find out the inverse function, then all you do is switch out the X and Y variables. And by the way, the linear function that we began with is a one-to-one function. So we have no restrictions on this process that I'm giving you now. So we'll be able to write the XY chart for the inverse function as -3, 0, -4, -2, -1, 4. Yeah. And then we're going to plot it. That's right. So we'll have -3, 0 as our first point. Thank you. We'll have -4, -2. -4, -2 is right here. Thank you. Appreciate that. Then we also have -1, 4. So -1, 1, 2, 3, 4. And we're here. And then connect them. There we go. Okay, so we have the graphs of both the original function and its inverse on this one Cartesian plane, on our rectangular coordinate system. Yeah, we do. And what else did I tell you about the inverse functions, guys? I told you that the line y equals to x would be the line of symmetry for your inverse functions. And it is. Notice that if you look on the upper half of the line y equals x, you'll see a mirror image to your original function. And once again, that line of y equals x is the line of symmetry for your inverse functions. And there is the graph proving, guys, that these two functions are inverse functions. Amen. Let's move on. What if you wanted to prove this algebraically, guys? Well, what can we do? We could find out what f composite g of x is. So let's say that our inverse function is this g of x that we speak of here, right? So in order to prove that f and g are inverse functions, we can use that composition method that I showed you earlier to say that we'll replace every x in f with this g function, 2x plus 6, right? So I'm going to rewrite it as 1/2 times 2x plus 6 minus 3. And what does that do for us, guys? If I take half of the values inside of the parentheses here, half of 2x is x, half of 6 is 3, and you'll bring down that -3. And then look at this. The 3's are canceling out to give you x. And that's exactly what you want. However, it's not enough. The g composite f of x needs to also equal to x in order to verify that these two functions are inverse functions. So what's going to happen now is I'm going to replace every x in g with the 1/2 x minus 3. Yeah. So I'm going to end up rewriting this as 2 times the quantity of 1/2 x minus 3 plus 6. That's what I'm going to do, guys. And multiplying 2 times 1/2 x, the 2's will cancel out, just leave you with x. Then 2 times -3 is -6. Then you bring down the positive 6, and what do you have, guys? After you cancel out those additive inverses, we end up with x. Look at that. So because our g composite f of x equals to x, and because your f composite g of x equals to x, then we have proven, once again, that these two functions are inverse functions. Amen. Continuing on. Problem number 4. Given f of x equals the square root of x minus 1, find the equation of the inverse. All right, that's what we're going to do. We're going to start off with our f of x equals the square root of x minus 1. We're going to keep in mind, guys, that this function has a domain restriction. The domain restriction states that x minus 1 must be greater than or equal to 0. How do we know this? Why do we know this? Because you can't have a negative value underneath the square root sign. It's undefined. So focusing on the domain, if we solve for x here, we can find the fact that x must be greater than or equal to 1. So we can write that as a restriction for the domain, that x must be greater than or equal to 1. In fact, we could go so far as to say that because our values of x would only be 1 and any value greater than 1, that your y values then would have to be greater than or equal to 0. See, if 1 is the lowest value I can plug in here, and 1 minus 1 is 0, and the square root of 0 is 0, then our value of y, at a minimum, would be 0. And since there's no boundaries on the largest number we can plug in for x, then there's not going to be any boundaries for the largest value of y. And this is how we can state that our domain is x is greater than or equal to 1, and that our range is y is greater than or equal to 0. Yeah, let's go ahead and write that out. That our domain is as follows, and our range is as follows. Now, we may need that information. So starting out the process, we will say that y equals to the square root of x minus 1. Then we'll be switching the x and y variables. So you'll have x equals to the square root of y minus 1. But we'll need to square both sides of this equation in order to free up our variable y. So you'll have x squared equals to the quantity of the square root of y minus 1 squared, which will cancel out that square root sign. So that we now have x squared equals to y minus 1. And then finally, what you'll do is you will add 1 to both sides of the equation. And you'll have y equals to x squared plus 1. And then keeping in mind the fact that we're going to rewrite this y as f to the negative 1 of x equals x squared plus 1. However, this is not your answer in its entirety. In fact, if you recall, since our domain is x is greater than or equal to 1, and our original range was y is greater than or equal to 0, that means that when we find our inverse, the domain and range will switch places for our inverse. And that will tell us that our domain must be greater than or equal to 0. See, the range of the original function becomes the domain of your inverse function and vice versa. And so the domain of our original function will now become the range of our inverse function. So when given the equation for the inverse of our original function, due to the domain restriction and the restriction on the range, you will have a restriction in your inverse function. Red box. That's right. We're going to red box our answer, including the domain restriction. That is important, guys, because otherwise you would be stating that this entire quadratic equation is the inverse of your original one-to-one function, and that's not the case. It is only a portion of this function that we need to express as the answer for this original problem here. Yeah. So this is what happens when your original equation is bounded by something, or if it's simply bounded due to the domain of the original function. In this case, we had boundaries based on the fact that the domain was restricted to x is greater than or equal to 1. So keep that in mind, guys. In problem number 5, they want us to find the inverse of y equals x cubed. Well, it looks like they want us to express this on a graph. Well, that's not a problem. Let's go ahead and make ourselves an XY chart. Okay. And with this XY chart, we're going to choose values like -2, -1, 0, 1, and 2. And plugging these values into the original equation, we will say that -2 cubed will give you a result of -8. -1 cubed is -1. Plugging in 0, you get 0. Plugging in 1, you get 1. And plugging in 2, you get 8. All right. Well, if that's the case, that means that our inverse function, all I have to do is just swap out the x and y variables from our original function. So that means that I have the first point written as -8, -2, that the second one is -1, -1, that the third is 0, 0, that the fourth is 1, 1, and that the fifth is 8, 2. Exactly. Now let's go ahead and graph it. Graphing the original function, guys, will show that at -2, we need to go down to -8. So let's say it's down here. Then I have a second point of -1, 1. I have a third point of 0, 0. I have a fourth point of 1, 1. And then I have a fifth point of 2, 8. So 2, 8 is going to be like right there. There you go. So here I have a graph of my original cubic function. That's what I have, which is a one-to-one function, by the way. See, it passes the vertical line test, and it also passes the horizontal line test, proving that we have a one-to-one function. To graph our inverse function, we're going to be plotting -8, -2. So -8 is going to be out here somewhere, and then -2, thank you. And then we have -1, -1. That's going to be right here. We're going to have 0, 0. That's right here. Then we're going to have 1, 1. That's right here. And then we have 8, 2. That's going to be about right there. There you go. So we end up with the following. Look at that. Look at that, ladies and gentlemen. So we end up with this cube root function. Remember, we said earlier that that would be what is expected from the graph of a cubic function when finding its inverse. And notice how the line y equals to x is the line of symmetry for these two graphs right here. Isn't that beautiful, guys? So if you're able to graph the original function by using an XY chart like we did here, then your inverse function is simply going to be the result of you switching out the x and y values. That's it. That's all you got to do. And so therefore, we have completed this problem right here as far as finding the inverse of y equals x cubed, which will be the cube root function. And by the way, you can express this as y to the negative first power equals to the cube root of x. There you go. There you go. Because this is the graph that you will see in red. Done and done. Let's move on. Here we go with problem number 6, guys. In number 6, we have find the inverse of the 1-to-1 function f of x equals the quantity of x plus 2 squared with the domain restriction that x must be greater than or equal to negative 2. Well, it appears as though they're giving us a domain, guys. So because the domain is x is greater than or equal to negative 2, let's say we write this in interval notation. You'll say that it is bracket negative 2 to positive infinity. This is the domain of the original function. And we can state that if negative 2 is the lowest value that we can plug in for x, let's see what happens in our function. Negative 2 plus 2 gives us 0, right? And then 0 squared is still 0. So the lowest value that you'll ever get for y is 0. And since we don't have any limitations on the upper values for x, meaning that the domain goes to positive infinity, then if positive infinity is plugged in for x, you'll end up with positive infinity for y. So your range is including 0 to positive infinity. And this is the answer for the range. Yeah, that's what you got there. So knowing this now, we're to find the inverse function. Keeping in mind that the domain of the original function will turn out to be the range of the inverse, and the range of our original function will be the domain of our inverse function. So remember that we're going to start by rewriting the original function by saying we have y equals to the quantity of x plus 2 squared. Then you'll switch out the x and y variables like so. And then we'll go about the process of solving for y. After switching out the x and y variables, you're going to go ahead and take the square root of both sides now. And when you take the square root of both sides, you won't need to be concerned about the plus or minus version of this, because remember, we're only trying to find the equation that is the inverse to this restriction, not the entire original graph of the function. This only takes into consideration the right side of this graph symmetrically. So when you flip it over your y equals to x line of symmetry, the only result that we'll need is going to be the result that includes the positive square root of x here. So that being the case, you'll have the square root of x equals to y plus 2 as your square root and square cancel out. And then solving for y by subtracting 2 to both sides, you'll have y equals to the square root of x minus 2. And with this, guys, you'll go ahead and rewrite this in function notation as f to the negative 1 of x equals to the square root of x minus 2. And this is going to be the equation of the inverse function, with the following restriction. You'll have the restriction that x must be greater than or 0, taking on the range of the original function for the domain of the inverse function. Red box it. All right, guys, so we have a red box here. So the equation for problem number 6 is done and done. However, let's see about the graph for these. When graphing our first function, remember that we can use an XY chart for this, right? So let's do just that. And we'll say that our values of x will be negative 2, negative 1, and 0. Let's use these values. When plugging them into the original function, negative 2 plus 2 is 0, and 0 squared is 0. Plugging in negative 1. Negative 1 plus 2 is 1, and then 1 squared is 1. Plugging in 0, 0 plus 2 is 2, and then 2 squared gives you a result of 4. So in graphing our original function, you'll have negative 2, 0 as your first point. You'll have negative 1, 1, so that point is right here. And you'll also have 0, 4. 1, 2, 3, 4 is here, so that we get this as our graph. Yeah, just like that. From here, what we want to do is find out what our XY chart would be for the inverse. And remember, in order to make that happen, all you have to do is switch out the x and y coordinates from the original function. So we can write our points as 0, negative 2, 1, negative 1, and 4, 0. That's what you have there. And then you will plot these 3 points on your rectangular coordinate system. So we'll have a point at 0, negative 2. That's a point right there. We have 1, negative 1. That gives you a point right here. And we also have 4, 0. That gives you a point right here, which gives us the following graph, just like that. And what did I promise you guys from the beginning? The line y equals x would be your line of symmetry for your inverse function. So notice, based on the restrictions, that we would only have this right portion of our parabolic equation, and therefore when flipping that over the y equals to x line of symmetry, you would end up with the following equation, which is equal to a square root function equation, right? So remember in our earlier facts, we said that a quadratic function would become a square root function as far as inverse functions are concerned. And this completes the graph of your inverse functions, guys. Done and done. All right, for problem number 7, we have a rational function in the form of a polynomial divided by another polynomial with the restriction that x cannot equal to 1 because that would make the original rational function undefined. So what we're going to do then is we can state that the domain of the original function is going to be from negative infinity to 1, not including 1, union 1 to positive infinity. See, we're excluding the 1 by not including any brackets in our interval notation. The range of this is where you can use horizontal asymptotes to assist you. That because the highest degree in the numerator is 1 and the highest degree in the denominator is 1, if we were to ignore the other terms and simplify 2x over x, you would get 2, right? So the range will run from negative infinity to 2, union 2 to positive infinity. So we would be avoiding 2 on the graph of the original function. Now, I did all that just to have the information. But as far as finding the inverse function, let's go ahead and say we have y equals 2x plus 1 divided by x minus 1. And then we're going to switch out the variable x with the variable y and vice versa. That's what we're going to do here. By placing x over 1, it gives us the ability to cross multiply now. So we can say we now have x times the quantity of y minus 1, which equals to 1 times 2y plus 1, which is 2y plus 1. From here, you may want to get your arrows popping. That's right. And you'll have xy minus x, which equals to 2y plus 1. Then you'll probably want to add x to both sides. Just saying. And subtract 2y to both sides. Go ahead and do that. All right. Be like that. From here, you'll have xy minus 2y equals to x plus 1 because the x is canceled out on the left and the 2y is canceled out on the right. Because we're solving for y, you want to factor out y out of the two terms on the left. So you'll have y times x minus 2, which equals to x plus 1. And then go ahead and divide both sides by x minus 2, and you'll end up with the following. You'll end up with y equals to x plus 1 divided by x minus 2. Well, isn't that interesting? Because that means that once I write this in function notation and have x to the negative first power of x equal to x plus 1 divided by x minus 2, we'll throw in the restriction that x cannot equal to 2 because that'll make it undefined. Red box it. There you go, guys. Go ahead and put that in a red box because notice that it is mandatory that you put in the restriction that x cannot equal to 2 because it reflects the original range of the given function, knowing that the range of the given function will be the domain of your inverse function. And there you have it, guys. This is the inverse function of f of x. And note how we said in the beginning that if you start out with a rational function, that the inverse function would also be a rational function, and it is. There you have it. All right, let's move on to our next problem. In problem number 8, it says to find the inverse function of y equals log base 2 of x minus 3 plus 1. Well, guys, looks like we have a logarithmic function here. And you cannot take the logarithm of 0 or a negative number. So as far as your original domain is concerned, x minus 3 has to be greater than 0. And in solving for that, we'll find that x has to be greater than 3. In interval notation, guys, the domain would be written as 3 to positive infinity, like so. If you're curious about the range of this logarithmic function, the range will be from negative infinity to positive infinity. And just keep in mind that the range will become the domain of our inverse function, okay? So what we'll do here is we'll start by switching out the x and y variables here. And you'll have x equals log base 2 of the quantity y minus 3 plus 1. From here, you're going to subtract 1 to both sides so that you end up with x minus 1 equals to log base 2 of the quantity y minus 3. From here, we can convert this logarithmic form into exponential form. So using this conversion, we'll have the base of 2 raised to our value of x minus 1 equal to y minus 3. And this is going to be our conversion from logarithmic form to exponential form. Now we want to still solve for y, right? So we're going to be adding 3 to both sides of the equation. And so that means we can say that y equals to 2 to the x minus 1 plus 3. And this exponential equation is going to be the inverse of our original logarithmic equation. Recall that you'll still need to convert this into function notation. So we'll have f to the negative 1 of x equals to 2 to the x minus 1 plus 3. And this is the equation of your exponential function, keeping in mind that the domain here is from negative infinity to positive infinity. There isn't any value that I can't plug into this exponential function. Yeah, so it works out. Red box it. So I got a red box right around my answer, guys. And that does it for problem number 8. So as a reminder, I would like to once again thank Elias Flores for his wonderful craftsmanship on the intro and outro on the visuals, guys. He did an awesome job once again. Let me know what you think about his intro and outro. And please subscribe to the YouTube channel Fort Bend Tutoring. Remember to click on that bell icon. And if you're able, please donate, as that helps us bring you more free math tutorials from me, Mr. Witt, and Fort Bend Tutoring. Peace.
Thanks for watching. We appreciate you hanging out with Fort Bend Tutoring. Like the video, comment, and subscribe. Hit up our website, tutoringmath.net, and set up a private tutorial with me and FBT.